Good afternoon. Good afternoon, everyone. Hello and welcome to this session. It's great to see. This is actually the best attended session that we've had of these Lunch and Learn webinars. So thank you very much for giving up your time for what I'm sure will be a really informative conversation. It's the first of our sessions that we're doing this year. You might have come across the previous ones that we've run, and basically we're running these series every sort of month or so, where we're looking to sort of bring in some expert speakers in particular areas to sort of share knowledge, start conversations, that sort of thing. So hopefully you will find this a really useful session. Just a little bit of housekeeping. We are recording the sessions, so most people look like they've got their cameras off. So keep them that way if you'd prefer. There will be an opportunity for questions, but if you can do that after both the presentations, that would be great. And then we've got two great speakers today. So first of all, we've got Dana Bazazayan, lecturer in machine vision and robotics at the University of Plymouth. Her research focuses on computer vision in the maritime domain, including underwater image analysis, marine monitoring, and AI-driven inspection technologies. And our other speaker, very pleased to welcome Pablo Borgia, lecturer in control systems and engineering at the university, and his work centres on non-linear control strategies for emerging technologies, with application in advanced automation and physical systems. And today's talk around computer vision and non-linear control in maritime applications will look at how those two fields are working and shaping innovation in maritime and autonomous systems. So I hope you find it a really good session. I will stop there and hand over to Dana and Pablo for you to kick off. Thank you.
Yeah, thank you very much. So I can start. Thank you for having me. So it's happy to just give this talk. So I'm going to kind of start the talk with some kind of introduction about the computer vision, just to explain that what is the computer vision and what are the applications in that. And then I will explain some kind of briefly some of the project that I'm involving by using computer vision in maritime. So in general, computer vision is any kind of process that we mimic basically the human brain to a computer to analyze what we see. So in similar to for any kind of visual data, images and video, we expect that the computer also have the same kind of understanding and perceive from the any kind of visual data. So there was more or less since 2012 and 2015 was a kind of breakthrough that by using all these kind of advances in AI and also the kind of powerful technology based on hardware and the GPUs and the graphic processors. So all these ideas for using computer vision and image processing improved a lot to have a kind of great improvement in that. And all these kind of techniques also are kind of multidisciplinary based on the math and neuroscience and psychology to replicate exactly all the kind of human vision. So similar to what we see and what we can understand. So with the computer vision technique is not basically just to recognize like the object recognition and the detection is any kind of scene understanding, any kind of conceptual understanding from any visual data is all under the umbrella of the computer vision. So I'm going to briefly explain some of the projects that I'm involving of using computer vision for maritime or underwater or any kind of marine science or marine biology application. So one of the very main kind of challenging with working with the underwater and the deep sea is that because there are many kind of noise and challenging and kind of disorder with the underwater images because the visibility is very low because of the light or the turbidity. And then one of the very kind of pre-processing important work with the working with the underwater images is to what we call it basically of removing water from the underwater data, because we can see all the colors as they are. So there are some kind of techniques for evaluating that, as we have a kind of color plot there. And then we try to kind of do the image enhancement to kind of increase this kind of resolution and the color visibility. So then we can kind of, based on that, evaluate that how we improve this kind of challenge there. And then we have some projects that are for the underwater biodiversity monitoring. So we track any kind of underwater animals, or so it's not just basically fish, as you see in this image. But then we can kind of track that and then measure this kind of biodiversity from the kind of the creatures that are underwater. And there are also some projects that
Dana,
yes.
Dana, sorry to cut in. I don't know if anyone else, but the slide that I can see is still the title slide, computer vision. I don't know if other people are.
Yeah, that's
seeing.
For me. It's the same for me. Yeah.
Oh, really?
Yeah, same for me as well.
Okay, sorry to interrupt.
Oh, no, thanks for saying that. So you just see the title?
Yes, at the moment, yeah.
Oh,
there
no,
you go. This one's got pictures of the fish on and so on.
Yeah,
so that looks like.
So you didn't see anything around that?
No.
Oh.
It looks like I can see the slides now, because on the left-hand side of the screen I can see your slide deck. Yeah, that's some fish with a.
But can like you see in the middle, or?
Yeah, you can see it in the middle as well. Yeah.
So maybe.
Then if you are using Linux, there's a bug in Teams. So what you need to do is to click on the Teams screen every time that you change something on PowerPoint.
But can you see this now? The images from the.
No, it's just black. It's just black now.
Everything is black now.
Yeah. Okay, can see that.
Yeah, maybe I just make it like this as a not full screen.
Yeah. Yep, can see that as well.
It works better, yeah.
Yeah.
Okay, so yeah, this was
if that works, you can leave it on. You can leave it on that screen. I think.
Yeah.
That looks pretty clear. Yeah.
So this was kind of the images that I showed for the underwater image enhancement. So the previous slides. And I was here, so talking about the kind of 3D reconstruction of fish for the size monitoring. So that was also a kind of project that we could measure the size and the weight of the fish. So that's based on kind of capturing with the stereo vision. So we have kind of multiple cameras, and then we could see that kind of measuring the size and the weight and this kind of estimation of understanding how the fish basically they grow based on like by feeding them during the time. And then there was also another project that we had based on the coral reef monitoring. So they are also some challenging that it's from the kind of marine biology side that is very important to kind of monitor that how are the kind of coral reef life under the ocean. So we had also another project that to kind of measure the size and segment them, find the depth, and kind of reconstruct that based on the 3D for the coral reef monitoring. And we had also another project that was with Pablo. So this was a kind of using the computer vision and robotic together to find the underwater trash detection. So from the computer vision side was basically to find any kind of trash underwater. And then that was a kind of developing a robot arm from the to kind of extract them and move them. I don't know if Pablo wants to add anything on this slide from the robot arm.
Yeah, probably I will explain a little bit more nonlinear control part of that project during my presentation, but just keep in mind that the idea was to have like an underwater robot, like trying to detect and remove pollutants.
Yeah. And the other project that we had was related to underwater telepresence. So this was more kind of using that as a kind of interactive with some co-design workshop. So the idea of this project was mainly to explore this from many people that we had in the kind of coastal area in Devon and Cornwall, that they lived most of their life in the coastal area, but they never had a chance to explore the underwater world. So for mainly like the old people, we made this kind of interactive underwater telepresence that they could use the XR or the virtual reality to explore the underwater based on that. And there is also another knowledge transfer project that we are dealing with, that is for the marine mammal monitoring with thermal cameras. So these are images around Plymouth. So we kind of detecting, like find the kind of life of the marine mammal, like whales and dolphins, that based on thermal camera we can kind of detect them, or even like in these kind of images they are completely visible, but in some sense that if they have just kind of blowing, and then we can kind of detect the temperature based on the thermal cameras. Yes.
Dana, sorry to interrupt again. Again, I don't know if this is
No
for others. I think the slide seems to be one behind what you're describing. So when you were just describing the
really?
and the dolphins, we were looking at the telepresence slide.
I'm really sorry. I don't know why this happened.
Looking at the pictures from trash. So at the moment,
really sorry, I don't know.
At the moment on the screen, you can see the one with the dolphins, and then this now is the coastal rip detection.
Can you see the coastal rip detection now?
This is now the ocean boat. The coastal rip protection was just the one before. That's now the dolphins, looking fantastic.
Is this the coastal rip detection now?
Not yet. No.
I'm really sorry. I don't know why this happened.
Okay.
Is this the coastal rip detection?
No, still got the dolphins. Possibly just sort of cancel and then reshare your screen. Perhaps.
Yeah, I just stopped the sharing.
Sorry, everyone. Just
yeah, apologies for that. I don't know. With Teams, usually works better.
Yeah.
Yeah, usually with Zoom, it's easier to.
Okay, so this is now the ocean boat.
Yeah, but I'm in the coastal rip detection slide. They still see the ocean boat.
Yeah.
What do you see now?
The iconic underwater telepresence.
That's weird.
I can see the coastal rip detection now.
Okay, so let's just stay there. so this was also another project that we had in collaboration was with the Met Office for the coastal rip detection. So as you can see, when there is a rip there, so we can kind of identify that when they are kind of two waves are moving, but they are not kind of joining together. So this was a kind of mainly the area that we covered with computer vision. but that was a kind of very bigger project that they tried to kind of connect all this data with some numerical data and from the kind of weather and the kind of weather forecastings. So then I hope it changed the slide to the ocean. Is the slide change or?
No, it's still the coastal reef detection.
I can't really understand this.
That's it. That's it. The ocean slides there now.
Yeah,
okay.
now it's ocean.
Okay, so this is also another project that is also with Pablo. So it's funded by area. So that's a project that we have. It's with the ocean company. So we use this for a kind of forecast drive. So they're controlling that, and also for the weather forecast from the kind of area of the when we have it on the ocean. So I don't know if Pablo wants to add also anything on this one.
I will also talk about formation control and multi-agent systems in my talk, but yeah, thank you, Dana.
Yeah, and then I'm going to the next slide. I hope you can see it. Is it changing in the slide or?
No, still ocean.
Yeah.
I
can see it. Can see it. Seems to be when you come off the full screen, you can now see what looks like a.
So it's a sargassum detection. So
yes.
That's also that's a project that we have it with because there is a kind of issue regarding the sargassum. Is kind of this kind of seaweeds that they appear in the ocean. So it happened a lot. It's kind of challenge in the Caribbean area. So that's using some satellite images to detect this sargassum, and that's also, I mean, another project that we have is based on the computer vision using the satellite images. And so can you see the wind turbines?
Yes.
Okay. So this is also something that I have multiple projects of using computer vision for the maintenance of the wind turbines. So it's covering that based on the aerial drones and the underwater drones. So with the aerial drones, we can find if there are kind of earlier stages of damages on the blade and also the body. And then for some kind of floating wind turbines, we can just find if there are any kind of damages like the algae or the other kind of thing that they can kind of attach to the foundation of the wind turbines, and we can kind of monitor that in the kind of different conditions. So that's it. Just I mean, briefly explaining some of the project that I had by using computer vision with the kind of in maritime or the marine science and the marine biology. And apologies for the technical issues. So I hope it was kind of understanding. And then if anyone has any question, I'm happy to answer, or we can move to Pablo's talk, and then afterwards they can.
Yeah, thank you, Dina. Thanks for persisting through the technical issues. It's always a bit disconcerting when that happens. So
no problem.
I think if people are okay, we'll hold the questions for after Pablo's session and do both together. So yeah, thank you.
Thank you very much,
Pablo.
Okay, so I'll try to share my screen. I'm also a Linux user, so let's hope that there are not so much technical issues as with Dana. Okay, so can you see my screen now?
Yes.
Okay, so thank you very much for having me. Actually, I'm very pleased to be here and give this talk. I will talk a little bit about nonlinear control in maritime applications. It will be a very informal talk. It's just a deck of 10 slides, I think. And it's more oriented to what, in my opinion, nonlinear control could bring to the table in terms of maritime applications. So I hope that this piqued your interest, and I will be happy to chat after, either via email or in the Q&A session. Okay, so my expertise is actually in nonlinear control design. So I develop nonlinear control algorithms. I also have some experience in simulating and modeling multiphysics systems. But probably this is not saying much at this point, because in my experience, when people think about the control engineer or control systems engineering, they try to put everything that they don't know where it belongs on that basket. So I will actually try to explain what I mean by control design, and I will try to motivate why I think nonlinear control is important in this scenario. Can you see my slide, by the way, the control design slide?
Yes, a toilet and a rocket taking off.
Perfect. So the toilet, it seems a little bit strange there, but what I want to motivate here is that actually you will find controllers and control design everywhere, okay? From your toilet, something related to your daily life, to rocket science, okay? So space rockets have also a lot of control, but your toilet, my coffee machine has controllers, your car, everything nowadays has a controller, or almost everything. Okay, your body has plenty of controllers. Okay, when I need to define again informally what control engineer means or what a controller does, it's actually the art of making a system behave in the way that you want. Okay, and to this end, you will implement something called a controller. So the controller will be this device or this algorithm or whatever that will make your system behave in the way that you want. So at the bottom of my slide, I have a block diagram where you have usually a reference, like the expected or the desired behavior. You feed your controller with that. That will generate a control signal. You would put that signal into your system, and that will generate an output. Okay, something that's missing in this block diagram and is very important is the feedback. Usually you feed that output back into the controller, and then the controller will make some computations in order to obtain the control signal again, step by step. Okay, well, controllers have been there for millennia. But I think the big boom of control theory started in the 20th century with the implementation of feedback. Okay, the op amps with feedback were like the big boom for control theory. And again, in this block diagram, a system can be, roughly speaking, wherever you want. Can be a motor or a power converter, or can be actually the economy of a country, or I don't know, the opinion of the population in your city. So there are lots of things, biological systems and so on. Well, so my talk is about nonlinear control. And if you have come across with some controllers in your life, you will know that there exists a lot of linear control theory. Actually, linear control theory, linear control approaches are well matured, and they are great. They allow us to solve lots of problems. In the past decades, the past century, they solve lots of problems for the humankind. So why nonlinear control? Okay, the first argument, that's probably the most immediate one, is real systems, real world applications are nonlinear. Real world phenomena are nonlinear. But okay, you can argue, well, I can approximate, roughly speaking, everything by linearizing my system or my plant. That is true, and it's a very valid argument, but then we have other things that we need to discuss, especially when you have, and that's an abuse of terminology, when we have something that is highly nonlinear, then the performance of linear techniques will be very poor. And in the worst case scenario, my system will be actually unstable. Okay, so where do I find these highly nonlinearities? When you are talking about mechanical systems, for example, robots or vehicles or ships or wherever, you have under actuation most of the cases. That means that you have fewer control inputs than actually the degrees of freedom that you want to control. That's one source of this high nonlinearity. It's not very evident, and I don't want to be very technical. But another thing, it may be strong couplings. So because this might be a little bit abstract, I try to include a figure in this slide, which is actually a soft robotic pendulum. So it's a soft thing, it's a continuum robot that will bend. And when things bend, that's highly nonlinear. The problem is you can approximate this using linear approaches, but it will not work great. And I will show you a video later about how this thing actually works. Okay, so I hope with this I convince you a little bit that nonlinear control is sometimes necessary. Now, why model-based control? Again, if you have used controllers in your life, probably you are familiar with PID control. And that will make a lot of sense because last time I checked a couple of years ago, more than 90% of applications were controlled using PID controllers. My coffee machine has a PID control, a PID controller, for instance, to regulate the temperature of the water. Fair enough. PID controllers are great, and most of the time they don't even require a model for the plant. So you can just tune them manually and hope for the best. They are very useful. Most of the cases, they will solve your task. Nowadays, we also have lots of advancements in machine learning, in purely learning techniques for control. So those are great. Those are trendings. But there are catches with PID control and purely learning techniques. Okay. So first of all, model-based control, it could be counterintuitive at the beginning, saying like it's convenient or necessary. Why? Because we need to start from the idea that all models are wrong. However, some of them are useful. Okay, so scenarios where I would like to have model-based controllers. First of all, if I know the model of my system, I can have simulations. So I don't need to deploy the real thing. I don't need to test on the real thing at risk of breaking something or making something to explode. I can do simulations. And that will give me predictability, and that will help me to actually understand or redesign my controller before actually test something in real life. That's great. The second thing is adaptability. Because, for instance, if we use purely learning approaches, then probably we'll spend a lot of time and data trying to learn something for a system. If I change my system, for instance, a crane, for a different model, I will need to restart the process, and that's time, and that requires a lot of data. In the case of model-based control, that's much straightforward because it's based on first principles. Performance. Okay, this is tricky because in general, in the long run, learning approaches probably will have a better performance. But at the beginning, most of the time, model-based approaches can solve certain tasks in seconds or less and very easily, while actually purely learning approaches will take hours or days to learn a task from scratch. Also, with model-based control, you can provide stability guarantees. So if you're trying to control, for instance, a nuclear submarine, probably you don't want the thing to explode. So you would like to have stability guarantees, right? In terms of the comparison between learning approaches and model-based control, we have also data efficiency. As you know, usually learning approaches will require a huge amount of data, and model-based control doesn't need that. And finally, extrapolation. Because you have a model that's based on first principles, most of the time you can extrapolate results. And in learning approaches, most of the time you will have a good result if you stay within the range of scenarios that you use to train your model. Okay? Well, these are some examples. This is a simulation of the soft inverted pendulum, the soft robotics. So it actually bends. It actually is highly nonlinear. Another example is, for instance, an autonomous vehicle that is trying to describe a desired trajectory. In this case, I chose a wheeled robot, but it could be a drone or could be a USV or something like that. And let me show you an example that I solved several years ago. I developed the control algorithm for this. It's an inverted pendulum. That's an academic benchmark. It's very common. But in this case, it was bending, okay? It was flexible. And that made the whole system very highly nonlinear. Well, highly nonlinear. I don't have proofs, but I cannot prove it, but I don't have doubts that this cannot be controlled using linear approaches. Okay, it was really challenging. But okay, I hope that I have convinced you about model-based control, nonlinear control, and so on. Now, the topic that we are really interested here is where does nonlinear control fit in the maritime landscape? Okay, so I think that will be the really important part for the audience. Well, again, as I mentioned, you will have actually controllers almost everywhere. So I just put here a list of bullet points of places where I'm sure that you will find controllers, but if you're a little bit creative, you can extend this list and make it huge. Okay, so we have autonomous and remotely operated systems, well, vehicles. We have wave body interaction applications. I will discuss a little bit more about this. In the case of autonomous and remotely operated vehicles, those are related to the projects that Dana was mentioning in her presentation. We have, for instance, surveillance and monitoring using drones, like the project that Dana has with the wind turbines. Energy converters. I actually worked here at the university in the control of a wave energy converter, for instance, ship autopilots, cargo manipulation, and vessel stabilization. Okay, so these are just some examples. And here in my slide, for instance, you have a drone that's transporting something, you have a crane that you will find lots of those in the dockyards, and you have something here. Well, that was my idea of drawing an OTEC. I think it's offshore thermal energy converter. Okay. Well, here we go. So this is just an idea of where you could find those. In terms of remotely operated vehicles, it's very evident that you can use those, or they are being used actually for exploration, for monitoring, or actually for maintenance even of certain devices. I took this image from Wikipedia actually, so if you are curious, you can see the application there. And this is an underwater vehicle, okay? Remotely operated underwater vehicle. You have an manipulator. All of it requires controllers. Second example are in terms of autonomous vehicles, you have on-crew vessels. So for instance, this is an on-crew surface vessel. And these are similar to the ocean project that Dana was mentioning before. And the remotely operated vehicle will be equivalent to the robotic arm underwater that we were trying to develop in the CROWS project, also with Dana. Okay. So when I talk about wave-body interaction, there will be two very specific cases that I will be interested in terms of the maritime landscape. The first one is vessels, ships, how they interact with the waves. So you want to guarantee that your ship or your vessel has good stability properties, can withstand the waves. And the second one are offshore facilities, like the wind turbines. Now, let me talk about something that I've been working on more recently. There's something called formation control. So this can apply for agents in general. I will talk here about just, let's say, boats or USVs, okay? So imagine that you want to make 4 agents to describe certain shape. So in this case will be a diamond. Okay, so you start from random like initial conditions, and they then form a diamond. And then the next step could be actually to rotate that formation and scale it. and everything will be coordinated. So you have a kind of swarm behaving in the way that you want. This is something similar to what we will do in the ocean project with them as well. And now imagine that instead of having the same model of boats, you have the same approach, but with different systems. You don't need to have the same model of USVs, for instance. You can have different models, or you can even have like aquatic vehicles and aerial vehicles. You could have some drones following, for instance, a vessel, or some drones following an USV. Okay. Here there are some simulations, for instance, of, a paper that I published, I think last year or this year, I remember. I think it was last year. So just to give you an idea how it works, we have 4 agents. We provided, okay, here is the initial configuration. The triangles are the initial conditions and the stars are the desired positions. And here I'm showing how they evolve in time in such a way that actually they are describing the desired formation, and they are able to move as a single entity without breaking the formation. Okay, so that will be one example of where nonlinear control fits in the maritime landscape. And with this, I would like to finish my presentation, and I think now it will be interesting to have some questions, and I will be very happy to chat with you. Okay.
Great, thank you very much for both of you. And just a very run-of-the-mill question: are you happy for us to share the slides afterwards? There's a question in the chat from someone early on. So
yeah, sure.
If that's okay, yeah. If you could send them through to Kath, and then Kath can pass them off to everyone on the call. So great. Thank you. It's really that was really interesting. Are there any questions from people? Please raise your hand or put something in the chat. Just to start off a little bit, and you both touched on this in each of your presentations in your own way. But I'm quite interested in how you see both of these fields developing over the next few years. I mean, you talked about offshore wind. Pablo, you talked a bit about autonomous vessels working together, and I was thinking there about the challenge from the first Sea Lord in terms of increasing the number of uncrewed vessels that the Navy uses. And I think the line that he uses is uncrewed where possible, only crewed where necessary. And so there's going to be a huge explosion in kind of autonomous vessels deployed en masse, and therefore the kind of stuff that you're talking about probably becomes even more relevant to keep them working effectively together. So yeah, a little bit from both of you on where you think each of these respective fields will evolve over the next couple of years would be quite interesting.
Would you like to start, Dana?
I mean, I just have a kind of general answer. I think mainly in the field of AI, computer vision, their things are just kind of improving and developing rapidly. So it's kind of in terms of accuracy and make them more real time with some more challenging scenarios. They are kind of constantly improving. So I mean, that's general idea. I don't know if Pablo has another answer.
Yeah, sure. About your question, well, in general, I think control will still be like necessary for lots of maritime applications. I think nowadays with the emerging technologies where we need higher precision, and especially with new materials and compliant things, for instance, where we cannot neglect like the non-linearities, I think there's a lot of room for these nonlinear control techniques. Like for instance, a nonlinear control technique could increase like the efficiency of the cranes used to load and unload cargo in the dockyards, things like that. But that will be a very general question, a very general answer. Sorry. In terms of what you were mentioning about on-crew vehicles, I think is very interesting because right now there's a lot of effort in doing this because the idea is you reduce risks, you automate more processes, and in the long run should be more efficient and cheaper. I think we are not there yet, but I think in the next 5 years, maybe, probably we'll see a boom here. And well, this is a little bit sad to say, but with the political and global landscape, I think also, I mean, the race has increased pace in case in this sense. Like everybody is putting a lot of effort in solving these kind of issues. So I will expect much more applications of on crew vehicles in the coming years, definitely.
Yeah. Okay. Thank you. There's a question in the chat around, can this computer vision tech measure emissions in ports, like from a smokestack, for example?
Yeah, that's a very interesting question, actually. I mean, I've never worked on that, but I think it's something that is feasible and it's possible to kind of detecting that. Very interesting application. Yeah.
Sounds like you might have found another project to work on there. So,
yeah. We'll add another slide there.
Yeah,
But yeah,
absolutely.
that's very interesting. Yeah, because I mean, it's something that is feasible to detect that with the computer vision techniques. But yeah, never thought about that. So very interesting.
Okay, I think we're nearly out of time. Another question here. With regards to a naval application, would integration with existing targeting systems be possible to alter the control system in real time, depending on a moving target's trajectory? Pablo, I guess that's one for you.
That's an interesting question indeed. I guess it really depends on what you consider real time. I don't think that in real time will be possible, but probably you could have a controller that is fast enough, if you let me put it in this way, to still solve the task at hand. So from a practical perspective, I would say yes, but it looks challenging.
I guess behind that is turning, from, I think in your presentation, if the bit that I recall was, you're talking about this partly helps you create a model from which to then predict for the future, and this is like looking at the applicability of that non-linear control in a real world situation. And I think you're saying there that there is a time limit to how quickly this can be applied, if you like, in a real world situation. Is that right?
I think that will depend on a combination of well, short answer is the limitation should be a limitation in terms of hardware, but still it will really depend on how you combine like an efficient algorithm with a powerful hardware. So always the limitation in terms of time will be dictated by your hardware.
Okay. It's pretty much out of time, so I can't see any other questions. So just like to thank you both again for the presentations. We will circulate them to everyone, and thank you to everyone for taking part. Hope you found it useful. There will be other sessions this year, so keep an eye out on the Freeport page, and we'll publicise details on there as we line them up. So thank you all once again, and hopefully see you soon.
Thank you for the invitation.
Thank you very much. Thank you. Bye.